and welcome to today's webinar. Our speaker, Dr. Moshe Ben-Talila, has over 14 years of experience as the manager of VisiMix's customer support. He holds a BSc and an MSc in chemical engineering from the Technion, specializing in reactors design. He also holds a PhD in chemistry from the Hebrew University of Jerusalem, with his dissertation focusing on practical methods for scale-up processes in the chemical industry. Dr. Ben-Talila has extensive expertise in technological transfer, having worked as a pilot plant manager and project manager in an API company for over 15 years. Dr. Ben-Talila has made significant contributions to the field, including his involvement in developing a BSc degree program in pharmaceutical engineering and writing the syllabus for the pharmaceutical engineering BSc degree program at the Azrieli College of Engineering in Jerusalem. He is also a lecturer at the college, teaching reactor design and principles of fluid mechanics. We're very excited today to announce in this session the release of our latest innovation, VisiMix Chem, for real-world chemical reactor dynamics. Please feel free to ask any questions in the chat box during the webinar. We will do our best to address them either during this session or via email afterwards. We hope you enjoy today's presentation, and without any further ado, I'll hand over the microphone to Dr. Moshe Ben-Talila. Thank you.
Okay, Marty, thank you very much to introduce me, and thank you all the audience to be together with us and to be in this presentation. This really is a new opportunity to contribute to the industry and to give more about what is the influence of the mixing in the process. As you can see here in the presentation, you see here flow patterns and molecules moving into the flow pattern, and exactly what we'll try to explain today through the software. And all these results, all these capabilities that are new, and connecting between the chemical reactions that can be, of course, enzymes and biotechnologies and fermentation, we can now connect with the real life of real life. The meaning of this, to consider mixing in all the levels, in the macro and micro levels, in order to progress. So the presentation to be mainly to present the product. It is not an academic presentation, but it will be around the chemical reaction simulation under mixing in sterile vessels. This is the topic that we feel in innovation that will be, we solve, and we were able to not only solve, to upload into a product and to provide it to you. I hope you will have opportunity to use the software and to enjoy with the very interesting result that I will try to show to you during the presentation. So we are really proud to present VisiMix Chem. The icon is like this. You see molecules moving in the sterile vessel under turbulent rate. And the main point here is that when we talk about chemistry and we talk about hydrodynamics, normally these kind of activities are controlled by two different groups in the company. The first group, of course, is dealing with the affinity chemistry, affinity of the chemicals association, and how they will generate the molecule. And it is, of course, very important. But when we go to the next step and we need to manufacture, we need to take in consideration the environment we're providing to these molecules to interact. This environment is the flow. And if we remember what is the flow, we are taking consideration that the flow is, of course, in turbulent regime more, is some kind of levels that we need to take in consideration. So we have a local level, fluid elements are moving into a tank, interacting between them. We have different zones in the tank with different kind of interactions, and we need to provide the direction on the flow and the power in order to generate this connection. So different kind of flow will generate different kind of connection between molecules, and What we succeeded to do is to represent, to include chemical reaction into all this frame. And what will happen after that, that we will have some deviation between a complete well-mixed equipment and the actual equipment. This is what we like to provide. So it will be a very good platform to connect between the professional people into the company that normally are working together, but in different fields. As you remember well, for people that are not don't know VisiMix is a Unix software because the software is based in semi-empirical models that solve the momentum balance to know the velocity of the flow. But in order to know the velocity, we have collected a lot of data that go to the deeply mechanical flow mechanics field. So we know interaction as a function of Reynolds number for different kinds of configuration. We include it into the momentum balance, and we solve this momentum balance to know the velocity of the flow. And once we know it, we're able to know specific results about the distribution of solids, liquid-solid distribution, and chemical. Now, in the chemical, until now, we take into consideration mainly the macro. What is the level of homogeneity in the macro point of view? But we now are including considerations in the micro point of view. So what is the influence of the really diffusivity and mass transfer inside the equipment for homogeneous, for miscible materials, okay? That normally we think that this is always close to the ideal way and it will be okay. And I will show to you during the presentation that this is not the situation, and it is solving a lot of problems that normally we have surprised after that how is this is happening. And our products are saving time and money. You know, mainly of the people that are here, I know you. I know I'm very happy to see you here, and you know well that it's very important to take in consideration the flow. And once you are taking it, you are solving a lot of problems that maybe will be a high cost in productivity, purity, and more. So this is the background of VisiMix. Only to remind you that these people came to Russia and they bring with them a lot of knowledge about the specific mixing. They are experts on mixing, they support the industry in mixing. And when they came to Israel, what the company becomes to be is to try to provide to the market this knowledge based in simulation and of course based in the huge data that they bring and the huge knowledge they have represented in the software. So all of this we explained before that. For people that don't know, we solve the momentum balance, the velocity, we adapt the theories of flow mechanics, and once we know it, we're able to calculate power per volume, mixing times, eddy size, and more. And after that, if you want to know more, you need to add more data. Until now, we add more data about liquid solid, liquid liquid, what gas liquid. We had about simple reaction. Now in this software, we will be able to upload many reactions. I will show many materials, and we have database for reactions for materials that maybe will help you in order to progress with your solution. So from year to year, from between 2 to 3 years, we are providing a new solution for the software. So it is complete list of times, table of release products that we released during the last 20 years, and we will continue to do, of course, according to the market demand. And companies working with us in different fields, you can see it. Some of them you know well, some of them are here with us. I'm very happy to see you here and more. Okay, in order to take in consideration the flow, we need to, in order to take in consideration the chemistry into the mixing, we need to define what is the scope of work and what we are able to do. The main surprise that normally we are thinking, we know is, that when we feed all the materials into the tank and in the lab, and we are progressing with our reaction, we see that it's taking, for instance, 2 hours to finalize, or 5 hours to finalize the complete consumption of the raw material. And now when we go to the production, it's taking 10 hours or 7 hours. It is not the same. And we are surprised because if it is completely, after a long time, it's completely homogeneous. So how, why we have different results, different kinds, different qualities? And this is the main focus we want to take in consideration now, because normally it's something that we think it's not possible. It's completely well mixed. We are in an ideal situation because mixing is taking, the reaction is fast, or is slow, sorry, and mixing is taking less time. Let's see what happens inside, okay? This is the point. As you know well, VisiMix is able to do a very fast result, so it will be a little easier. No 1 millisecond, it will take about a few seconds, but continue to be in the complexity of the work that we're talking, solutions in the position and in the time, it will continue to be very fast. And once we have this information, because we're bringing the data from the lab, we will be able to connect between lab and production, analyze better the way to operate. We're taking consideration the concentration, the feeding position in the tank, the mixing design of the tank, and the solvent, different kinds of solvent that will be, of course, we have different kinds of physical properties and will affect dramatically the capability to connect between the materials. So VisiMix gets enables a user to look at the real world mixing reactor by obtaining reliable information about each reactant concentration and conversion. So we are talking about results. If we, for instance, the reaction is A plus B, give me B plus byproduct, okay? We will be able to know what is the actual situation in the tank if the process is continuous, what is the actual outstream, okay? And how is connected with the process that is like ideal. But it is impossible to have ideal, because we are not talking about molecules. We're talking about fluid elements. So when we have a minimum fluid elements, that it happen anyway. So we are competing with this kind of result, and not for a situation that normally is impossible to have. We are not putting molecule one to the other one. It's not happening in the real life. But we know what is the minimum fluid size that we can get. It's like the ideal, and we will compare it with the real life. So we are talking about average concentrations, and we are talking about a conversion, okay? If we have A plus B, give me C, or A noten B and B noten A give B and B give C, we can talk about conversions about to equipments, to raw materials, and we can explain about what is the non-uniformity that we have into the tank, that give me an idea about how far I am from the real, from the well-mixed equipment in the macro point of view and in the micro point. And other kind of results that you will see a result that is a concentration as a function of the time, where we will present always two graphs. One graph will be the reactor with perfect macro mixing. That is that I explained before that we see that are homogeneous, but maybe the local diffusivity will be different between the materials. And we'll present the other graph that is the real result, when we take in consideration the maximum diffusivity or the complete diffusivity that happened in the tank. As you can see in this case, that is very surprising one, but it's a real one. We have better results with the actual reactor than the real reactor, and it happened. And it is a surprise. Not always happen, but when it happens, for us a surprise, because we think that the ideal is perfect. No, sometimes the ideal is not perfect, and we will have better results when it is not ideal, because we are promoting some kind of reaction that in average will be less than when we have a place that the local mixing is worse or better or good for the reaction that we are working on. Okay, so this is the kind of the results we will be able to provide. And of course, the connection between the chemist and the engineer will be more clear, okay, for everyone. Remember that we're working in true regime. And if you remember that when we explain how to work with the software, and we talk about the laboratory coming to some bench scale, that in this bench scale, we are trying to characterize the process. And we explain that the better way to work is to know why we're working in the production step. And after that, coming to setup in the lab. Now it's relevant because now we can talk about different kinds of solvent, different kinds of concentrations, and continue to calculate the real reaction. So it will be clear for the people coming from the chemical field to understand what is the meaning of even some change in the solvents, in the chemicals that we're using, and of course in the mixing that we will have after that. Okay, so this is very interesting too. This methodology I explained many times, and we can go deeply more for companies that don't know about it in a tailor-made presentation for everyone. Please contact us, and we'll be very happy to provide to you for your company specifically more explanation about it. Now, VisiMix Chem, what we're able to do now, we will able to feed up to 8 components. So we can define the components, okay, the name and the name of the component with the molecular weight, and what is the initial concentration into the tank or in the streams that are entering to the tank. We need to define the temperature and the molecular weight because we need it for the diffusivity, the molecular diffusivity. We're able to set up about 5 chemical reactions that can be reversible reactions. So the meaning of this is that we have about 10 reactions, okay? 10 reactions, as you can see here in this example, you can identify this is the enzymatic reaction. This is a substrate with enzyme will be the complex of substrate enzyme. The substrate enzyme give me some product, okay? This product is divided in 2 after that, so we can really talk about the complete characterization of the process mechanism in the chemical description, and progress with results that sometimes will be very important to avoid problems and setting up the conditions that are required for the process. So 5 chemical reaction. It is possible to include catalyst and innovation or innovation, and include into the reaction rate the catalyst and innovation according to some correlation that you can find. And we will continue. And the results that we're providing are the following. For processes that batch, semi-batch, or continuous, comparison between the perfect mixing, in this case it's opposite. In this case, the actual is the perfect macro mixing is better than the real life. Okay, but compare between them. This is very important in table, in graph, and in table. Okay, the process can be the result will provide conversion and concentration for batch, semi-batch, and for a continuous process, as you can see in different tables. We have included something that is new, normally not in VisiMix, that we have the database inside the software. So we have database of equipment, liquid, process that we can connect with keywords and description of that will be simple to have some searching about it. And we have another database that, for instance, you are using always the same solvents, and you are using some raw material for different kinds of process. So you can define the material and only bring the material for your new process, and not to feed again and again the data. So this is the database. All is possible because the framework, the infrastructure that we're using we use in this new release is a new one, more modern, and give us a capability to give you more comfortable results. Okay, what is the field of the application of the program that we're presenting now? The software input support the convenient format of entering chemical kinetics into the simulation. So we will need the chemical kinetics. So you know how to do it. You have a process. You can take you have the materials inside, and you can take samples as a function of the time and know what is the concentration of the reactants and the products. And once you will have this curve, you can do in fitting of the curve that will give you the order of the reaction and the kinetic constant of the reaction, so this will need. Chemical composition of the inlet flow. As you remember well, VisiMix is able to know what will be different result if we fit close to the impeller or in the top of the tank. And it is really important we are able to do it. Now we're able to do it and include more defining well the diffusivity, not only by the non-uniformity into the tank. So we include another model that will be more precise. And of course, all this mixing system design that, if you remember well, the tank difference and the impeller difference, impeller that can be completely different one to the other and continue to provide you results. Okay. Now, the VisiMix Chem is working now in turbulent. Okay, this is the main use now. What we are doing is using the model that we have about hydrodynamics. We evaluate hydrodynamics according to the input data. We focus ourselves in the energy of dissipation that it is defined in the size, calculated by a Kolmogorov or the connection to the Kolmogorov eddy size, and it gives us a capability to determine the macro mixing and the micro mixing characteristics. So we are talking about two levels. The first level is how the material is moving into the tank and how once at every place, how these materials are connected between them. We connected with the reactor with perfect macro mixing. The meaning of this was assume that the macro mixing is perfect, but they continue to have materials that have different physical properties and they will have different diffusivity. Okay? This is the point that we are this innovation point. So the rationale of the way to calculate is using the sign characteristics of the reactor, calculate the primary hydrodynamics characteristics such rotational, radial velocity, radial and axial velocity, turbulent energy dissipation, and turbulent diffusivity for different kinds of zones into the tank based on the primary characterization of the turbulent flow generated by the step one. Only feed that and click enter to generate the result that we know before that. Obtain the secondary flow characteristic covered by the macro and micro mixing into the tank. After that, get because we feed materials, get the local concentration of reactant based on the hydrodynamics and micro mixing. And once we have it, we will be able to compare these conversions and these results into the different equipment in the industry, because once we know that the reaction is always the same, it's not to take care of where it happened. The chemical reaction is not a function of the equipment, but the environment we're providing to the reaction can be different, can generate deviation in the results. And then this is the point that we can, of course, go to scale up, industrial scale, and generate good results. The deep explanation about what is the model is explaining in the brief description of mixing phenomena. I have uploaded the presentation here, and you will see this presentation after that in the website. You can download and see. The main activities is to include the local diffusivity by Kolmogorov estimated size and the eddy size, and by definition about what will be the influence of the micro mixing into the tank and what will be the influence of the micro mixing into the tank, because we will have there inside eddies, inside every eddy that's moving and generating the macro homogeneity. What happened with the internal diffusivity into the eddy zone. I will not go deeply about it. It's very interesting to do it. I include another 2 slides showing you that we are able to take in consideration fluid elements in different kinds of configurations and understand why in the same time, as you can see here, the fluid elements and will be completely different distributed for different kinds of equipment, and this can give us at the beginning the macro time will be different, and after that the connection between them will be different. So this is one of the points. You see 2 equipment with the same volume but different geometries, without jacket and with jacket. You see completely different flow that will generate completely different interaction between the materials and different eddy size. The second point is to take in consideration that once we have material A and material B and you start to move, and you are doing some kind of eddies, when you put these eddies, you see concentrations of A and B, and they will diffuse. This is the local mixing, okay? And we are able to calculate with the equation that I showed you before. Of course, all of this, we can go more deeply about it, but this is the main idea and framework. Of course, we can work more. All of this information, the first 2-3 slides, are in the help into the software. So when you open the software and you want to know more about what is the basic background, the scientific background, very basic one, you can go to there and you will see it is explained here in the presentation. Now, what I would like to do is to remind you something that we do sometimes. I want to show to you what happened in a reaction that when it's clear, when it's all the material are dissolved well. So we have water with Ki, Ki3, and NaC. And when we feed HCl, if we are dispersing the HCl in a very good way, we will see a change of ions, but without color. And when we don't spread well the HCl, we will see iodine, and this iodine have a color, and this will be the difference between good dispersion of material HCl when we feed HCl to bad dispersion. And I want to show to you this video that's showing you how it's working. Okay. Sorry. I hope you can see. You see, it is very big one when we feed the material. But if we will start to do stirring, okay, a low velocity, and far to the impeller, what you will see close to the deep pipe here is that you will see a color that entering, and all the material here inside. You see now the color here. Okay, the meaning of the, and all the media is changing the color. And if we continue to go close to the impeller and very fast velocity, this is what we have here, you don't see color, you don't see nothing. Okay? And it is what we want to show you, that it's possible to calculate it in a good way and in more precise way. That is what we're describing now. How is working? It's working in this way. The first window is to define the materials, define the molecular weight, and define the concentration into the tank, and what is the feed, the concentration into different feeding position. We have 2 feeding positions and 1 output outlet if it is continuous flow. Define the temperature, define the molecular weight, and define the type of solvent. It can be polar or non-polar, organic or non-organic. We change the way to calculate the molecular diffusivity. After that, we can define reactions. In this case, we have 5 reactions. In this case, it's like a enzymatic reaction. Every one of them inside, we can define the name of the reaction and what is the name of the reaction designation and the name of the reaction. We can include here stoichiometric coefficients, okay? And include here the reaction rate and the order of the reaction. We can include catalyst, okay? And include into the reaction rate the catalyst influence. And the catalyst can be one of the components, not only, you can see A, one of the input here. And it can be in a reverse reaction with the kinetic of the reverse reaction, and it can be, of course, opposite the inhibitor. Okay? All the description about the units are here in the window. After we finish to define the reactions and the kinetic of the reaction, we can define what is the flow and the change, of course, the flow in the inlet positions, okay, and how long I want to calculate, okay, how long I want to calculate the process, okay, for the transition duration in the continuous flow, or for all the process in the batch or semi-batch flow. And we need to specify, as you remember, this is not new, but if you remember well, we were able to specify where we locate the the inputs, okay? Where did we locate the inlet number 1 and the inlet number 2, and we define for that what is the concentration and the flow for every one. Once we do it, we click enter. After a few seconds, we'll get the reactor with perfect macro mixing, but continue to have different micro mixing because it is the molecular diffusivity. And what will happen in the real life, that not only the macro mixing is different in different places, and the macro is distribution is different. We have non-uniformities there. This is one of the results. The second result will be every material, what is the concentration, what is the concentration outside, and what is the concentration if we take in consideration like a perfect macro mixing reactor. Okay, that is it is not well mixed definition, but it is the well mixed as possible in the real life. Okay? And what I will show to you now, I will open the software and show to you. The first example is when we feed the batch reaction and we change the impeller velocity and we change the solvent. The second, when we have more than one reaction, and what will happen when we have only when we have multiple reactions and in different feed position. The other examples you will get when you have the software is when we have multiple impellers in the same shaft, and this can change the results. And the last example, and all of this you will get with the software when you will acquire the software. You will see what happened with the biotechnology or enzymatic reactions. So how you can feed all the mechanism of the process and generate results. All of this is moving very fast. So this that I will do now, only to remind you that we have a line of products. So we'll include now VisiMix Chem. In the website is included VisiMix Chem with all the explanation. And we invited to come to see all what we have in the website, to see testimonial of companies, and to remind you always that when we talk about VisiMix, it is not a couple of correlation that you can find in the literature. It is, of course, not a pure mathematical solution of some differential equation. It's really an expertise, it's a knowledge that we are trying to provide to you through and to solve the mixing by combining all what is possible, the empirical data deeply to the friction factors and all, including into the differential equations in order to adapt this model to the stirrer vessels. And once you have the results, we prove the results, and we see that the result is representative because we add our value, our knowledge about how can be the results. All of this is included, so it's a mixing expert trying to provide you through the software the knowledge required to progress. Thank you for this part. Now I will open the software and show to you how it's working. And in the presentation, you will see more, okay? In the presentation, what we will see more is more some kind of a summary of what normally we present to you when we talk about mixing by cell. Okay? So now, with your permission, I will open the software. We have some questions here about the conversions and all. I will answer at the end. Okay, thank you, Cluly. I will answer in 1 minute. Okay, after we finish. Okay, so the software is this one. Of course, it is starting on beta. It is the first version, or we will improve more the version, but this is the first starting version, and because we succeeded to do some job, so we wanted to release at this stage because the main science is there, and it's important to show. So when we click there, what you see is a little different background here. You see VisiMix project that you can open, and you can see here all the calculations that we can do. The first to do is to go to the database tool and open database for the projects that you have. For this, you can select one of the database or create a database. The meaning of this, when you create a database, you need to give some name of the database with the some 4 fields that are we advise to use this field, but you can use any field that to identify the project, okay, or the database, because the database inside you will have many runs about your projects, okay, and or to use one of the database that you have ready to use. I have here 4. I will use this one, and we need to click set activate, okay, and click OK in order to now we're able to retrieve from the database projects. How to do it? When I click project open, you see the software show me all the projects that I have in my database. Okay, you will receive all of these database, okay, from 1 to 4, and you have here the description of every one of them. What I will do now is to start to feed the data from the beginning to give you a complete idea here. Of course, this data is ready. Okay, you can open and you can see all. Now, when I click project open, I can select, for instance, the demo 1.1 and to compare, okay? Or demo 1.2 is the same, but with different velocity, or with different solvent, and the third is the same, but with different velocity. What I will do, I will, instead to retrieve from the database, I will click new, and we'll give the name, okay, will be for the presentation, okay? And it will be presentation. Only to give you an idea, here you can give the name of the project, the importance, where it's located, etc. Once we click OK, the software opens the capability to input data. Until now, it's not automatic, but it's very intuitive. If you come to edit input, you see you have the chemistry, the equipment, the process, and the physical properties of the method. So the first is to come to the chemistry. In the chemistry for our process, the process is the temperature of the process. Let me check. Where is it? 1 minute. Yes, is we can go in Kelvin, okay, and it's 322.15, okay. The molecular weight of my solvent in this case is like water, but we can select any one, and the solvent type is water, okay, inorganic. It can be organic, inorganic, alcoholic. And now we can design the material. For instance, material A, okay. The name of the material A is alcohol, okay. And the molecular weight of this material is 32 gram per mole, and the initial concentration of this alcohol in the tank is 1.2 mole per liter. Because it is batch, this example is batch, I will not feed in any feed. I will not feed that. Okay. B. Sorry. Yes. B. The name will be acid, and the molecular weight of this acid will be 760, and the quantity, the concentration is 1.2, and the material, the product in our case is C, and it will be an ester, and the molecular weight of this ester is 74. And of course, I don't have a concentration, initial concentration in the tank. Okay? Once we click OK, we need to go to the chemical reactions and define the reaction. So I click add here in the, to add the reaction, design the reaction, for instance, is R1. R1, the reaction will be esterification. Okay. And here we can select the reagent A, reagent B, and reagent C. C is the product. You see that it's reversible reaction. here we can add the stoichiometric coefficient. In this case, we have not a stoichiometric coefficient, or everyone is 1. If we don't fit nothing, the number will be 1. We can add some inhibitor or catalysator, okay, and define, okay, when you define one of them, we need to define the in front of this catalyst. In our case, we don't have it, or it is not important for us. And the reaction rate coefficient is 183, and the order is 1. It can be any order, okay? It can be 0.5, 1, 2, 3, 4, what you want. The reverse reaction is 32.7, and the order here is 1. So we have a reversible reaction, okay? We have A plus B gives C, and C gives A plus B. And we define every one of them. Now, once we click OK, you see all the reactions here. When you see this point and this B, the meaning of this all is correct inside. We fit well, and we can continue to fit more. I will show to you in the other example that we have more. It's the same way to work. And once we click OK, we define to fit all the input data about the chemistry. Now we need to go to the mechanical design. Now here, you know, well, tanks all, but we have very good news here, because when you click project, you can import VisiMix turbulent project. So if you have project that you already done, and you have the file ready, but you need to include to evaluate the chemistry with more modeling about mechanism about the chemistry, you can start by importing this data with all the VisiMix file that we have with all the data with the VisiMix file, and you need only to include the chemical reaction, so you don't need to feed again. I am doing here now to everyone because some of you are not familiar, and we have some news on the mechanical design. When you click the tank, the software is asking you about the tank. If you click, of course, jacket, if it is not possible to fit with jacket, because until now the software is without heat release. We can include the heat release according to your requirement. Of course, it will take time, but here now is for isothermic reactions. In the tank that we are working here, the total diameter of the tank is 1,000. The total area of the tank is 2,000, and of course the volume is completely clear because it is the function of the diameter and the height. And the volume that we are using in our the level of the tank was 1.6, sorry, 1,600, and it gives me, when I get there, it gives me the volume of the tank. Okay, with the dimension that you know from VisiMix is not. Now you click OK, the software is coming. You need to go to the buffers. In this case, we have no buffer. Okay, and when we come to the impeller, now you see the impeller that we have here. The viscoflux flux is new one. Alternative impeller is continue to be here. All the hydrofoil prototypes. So we included another one that is useful. We see some companies that are using it, so we included, and it's special one for this. We included now, and it's available for you. In our case, I will use pedal, and when we use the pedal, we need to provide the data for the impeller. So the type diameter is 500 millimeter. The number of blades are 2. The width of the blade will be 110, and the distance from the bottom will be 305. We have one impeller. It can be multiple impellers, and the velocity is 6 RPS, that is 360 RPM. The motor power is 1119. Now we click OK. Now we feed the chemistry and the equipment. We need to feed the process, and our process should be as the following. The inlet input location, okay? It will be, for instance, for material in the position 2, it will be 0.5, okay, sorry, okay, 500, not 0.5, it's 500, okay, and the I will be 500, okay, this is the position, the coordinate of the position of the input, and the output will be, for instance, 500 and 1,500. So you can see that we can define inlet and outlet, for instance, 0 and 0. Okay, so we have all the inputs and outputs. Now, when we click OK, we need to feed the feeding here because it's batch. All is 0. Okay, and because all the material is inside. So we can define the flow and the time that we are feeding, but in our case it's batch, so we click 0 and we want to run the process, for instance, 300 seconds only, to not take long time, okay, only to do it fast. And once we click OK, we can calculate. Because we are in batch, the first that we can calculate is the final average composition of the material that I feed. You remember I feed A and B, and we'll get the results. When we click OK, we need to define, of course, density and viscosity of the media. I will use material, okay, that is, for instance, with this density, and the viscosity I will use 10, okay, because it will be interesting. It can be 1, okay, but I want to use 10 to show you something that is very interesting. When we click OK, the software is processing all and will ask me to run. When I run, you see how is the progression of the calculation. We put it in order to give you an idea how we'll finish. Okay, a few seconds. It's not taking 1 hour. A few seconds we'll finish. And what you will see is something very interesting, is that when we have all the material inside with this solvent, this viscosity, we have a solution that will be okay. These are the expected, yes. I have actual reactors of the results, okay, and the product C, okay, and in the perfect mixing is the same. Okay, this is that normally we think when the materials are inside, we have no deviation between the actual and the real mixing, and even we can see it in a chart. For instance, if I see the chart and I select material A, you see that it's taking like this. We have half conversion, about 50%. Good, yes? But if I do clone, okay? If I do clone, okay, it's clone. And now in the clone, I only will change the RPM, okay? And instead to have 360, we go to 0.5, low velocity, okay? We can assume that the process is, will be the same results, yes? But when you click OK, and you ask to calculate the concentration of A, okay? It will, of course, ask me to run, okay? Now you see that is completely different. Even if we think that was homogeneous and exactly the same, we will get the same results. You can see completely different results. Okay, but it is batch. It take put 5 minutes, but it can take 2 hours, and it is a typical report that we get. You did, you know, I did in the lab. It take me 5 hours, and the production take me 10 hours. Yes, because the diffusivity inside is different. Even if we think we're in batch and all is homogeneous and all is okay, we continue to have different results. Okay, and this kind of result can be different in different ways. I want to show to you only what happened when we use, it is the same process, but we use I open 1.1. The only difference here is that we have a different solvent, okay? different solvent, okay? Let's do different solvent with all the same. Only we change the density and viscosity of the solvent, okay? And you will see that the results will be completely different. Okay? So we can interact with the chemist and show that it's taking consideration even the solvent, okay, in the process. And after that, I will open the example that we have different positions, and the other two, of course, will show to you in your specific presentation for the company that will be tailor-made. Okay, this you can see that it's lower because the diffusivity is different. I do low viscosity, so the eddy size is smaller, so this is taking longer time. So you see now the numbers here are different. It's not 0.7, it's 0.8. And now, if we calculate the chart of A, now you see immediately change, different, zero, we finish, okay? So you can see how different is with different solvent or different velocities. The last point that I want to show to you is the example number 2. And example number 2, as you remember, we have the reaction A plus B gives me P, and the 2A plus B give me byproduct, and my equipment, okay, my equipment is a pedal, okay, with low velocity, and I am feeding in different positions. But I want to show to you these results. I want to calculate the A is a function of the time, and it will ask me, of course, to run. Okay, I need to change something else. I need to change, sorry. I need to change the time. The time was 1,200. Okay. Yes, sorry, my mistake is in continuous flow, okay? And I want to know the chart A. And now we can run. And what happened here? This is the perfect mixing, as you see how it's going up and down. And this is the real mixing, the actual real mixing, okay? If I open and feed in different position, okay, if I open the process, okay, in different position, okay, and run the process, know what is A, you will see completely different results. It is the powerful of it. Now we know to explain how we are dealing with reaction into the real life. That it was very difficult to solve, but we finally solved. And this is what I want to show to you. Of course, we have a report, and we can send this report with this complete Excel report that we can get. And with this, we will finish this part. If you want more tailored presentation about all the examples we have here, we can show to you, and we can fix the time. Of course, people that are starting to work with the software and will require to have the software will have for the release time a very good condition. So customers that are our customers, we provide, of course, results. What you can see here, it's really interesting. Yes, the perfect mixing time, the perfect mixing reactor is going in this way, okay? And we didn't finish the raw material, okay? And with the actual reactor that we fit in different positions, you see how it's going down. It's completely different than we got here, okay? And this is the powerful of it. It is exactly what gives us the capability to have a very good understanding about how is the influence of the mixing the process in the chemistry, and to help to help to understand that it's not possible to, even if we take some ideal situation that is not the well mix, it's not existing, but in some well situation of mixing in the macro mixing, continue maybe to have better results in the actual reactor than in the what we supposed to have ideal reactor. And only to show to you, if we click report, we can generate this report, and I will put it by desktop to show to you. And when I have it ready, I can open it in Excel, okay? And what you will see in the report, yes, sorry. What happened is not working, not opening. 1 minute. I don't, oh, sorry, I don't see the report here. Maybe in the, so in the report, you will see all the data in line with the results. For some reason, it's not opening now, right now. Okay, so we reached to the end of the meeting. I hope you enjoyed the meeting. We have some questions here. I will read the question, try to answer. The software is able to simulate conversion based on kinetic information input by the user. To clarify, is it able to do opposite, to fit simple model to experimental data obtained by kinetical patterns? No, the software is mixing software and we need input that is the chemistry. The way to get the kinetic reaction, the constants, the order and the kinetic reaction constant is by doing some activities in the lab and try to do some fitting between the points you get and the order to do. It's pure mathematical algorithm. That can be, it's not so complicated to do if you are doing this fitting and there are algorithms to do it, okay? But once you have it, the main value is that really you are getting solution about what is the sensitivity of the flow into the reaction. Very interesting product. Hello, Cliff. Thank you to be with us. Very interesting product. Can it address the solution of solids, for example, to estimate required time? Yes, but this is what we have in the actual VisiMix. If you go to the actual VisiMix, we have a mass transfer liquid solid, and then you have this data. Of course, we can combine it and to compare between the reaction that were completely homogeneous, so not homogeneous, completely dissolved, and to compare with the mass transfer that we get when we calculate in the software, in the VisiMix, actual VisiMix, that this we have in the software, in VisiMix by itself. Does the program account change of physical properties during the reaction to increase the velocity? As now and until now, no? I hope, and it is very fast for this we're not doing because you can generate, you change the viscosity and after 2 seconds or 1 minute you get the result, so you can collect in 5, 6, 7, 8 different viscosities, and you can put in the Excel and you will get. But we are working on it. We hope that the next release that will be some project that is not so complicated project, is more to help you to analyze results, is to do this work. We will do some kind of sweep where you feed some input from 100, from 1 RPM to 100 RPM, step by 10, and generate results. So you can change the viscosity and it will take in consideration the change of the viscosity. Is very fast. Hi, Amando, to hear your question. Thank you for the presentation. You talk about macro and micro mixing, but what about meso mixing, intermediate eddies or in feeding zone? As you can see, we are taking consideration. The second example that I showed you was very fast, but I show you is a different feeding position. So we know about the feeding position, what is the influence in the tank, not only because we have macro mixing moving, is because the drop that's entering there is experimenting some diffusivity and some eddy size and Kolmogorov eddies that will influence the local interaction. I know that there are models about mesomixing. In VisiMix, way to calculate and way to think, the mesomixing is something that is difficult to prove. And instead, mesomixing want to guide you about how to select the feeding position. we talk about main period of circulation. That is a parameter that is simple to catch. Okay, this is the flow, the flow in the tank by divided the volume of the tank with some, of course, real pure number. Okay, take in consideration the cycles that the flow is doing into the tank. This is the reason that we are not taking it, and you can see it's really representative and well. It's different way to think. Okay? We're aware about mesomixing. You can take, for instance, all the data that VisiMix gives you about the eddy size and energy of dissipation, and including the theories of mesomixing, you will get numbers. But normally now, when we have it, I think it will be not so required. We can discuss about it. Does the program account? Okay. Okay. So this I wanted to show to you. We passed 5 minutes more than the scheduled time, but you can see impressive results, surprise results. Even if we don't see in the example number 1 that we have deviation between the actual and the so-called perfect mixing, when we go to different situations, we have completely different conversion. When we fit the different position, we have even change dramatically the importance of the micro mixing, the real mixing, instead to the so-called perfect mixing. And you see that it's opposite. Okay, so opposite way. So it is really answering a lot of questions that normally we work and we surprise when we go to the next step. So thank you very much to be with us. It was a pleasure to be with you. I'm very happy to see you again, all our customers that come to here. I cannot give the name of everyone, but I identify you well. People that are new, you are invited, of course, to contact us. We will do a second session and we will focus more in the examples and invite more people. It is really innovation for the simulation in chemical reactions. It's a unique way to do it fast, get results that will be representative. So thank you very much to be with us. And we will see you in other opportunities, in other website about this new innovation in the market. Thank you very much.